There we go. Yeah.
Sounds good.
Cool.
I wasn't really sure how much depth of information to go into. So like, did all three of you kind of read through the chapter quite thoroughly, or?
I did. It was quite long, I thought. I think the one thing I also did at the start was he mentioned in the appendix he had like a sort of checklist.
Yeah.
And I think I actually initially went to that first, and then went back to the chapter.
Yeah.
But I did find once I started getting to like the code examples, it was fairly straightforward. Well, straightforward. Yeah. It was just a lot of typing up, but I felt like it was, it was quite well organized. But
yeah, I definitely agree with that. Okay.
I downloaded the Anaconda distribution for Mac, and I'm using the Jupyter notebooks that come installed with it. So then I just downloaded the Jupyter notebook file for this session and for the last session, and that was, I guess, pretty much everything is in the Jupyter notebooks.
Yeah, that's great.
Yeah.
Okay.
I was going to say, actually, I did find myself sort of just making extra comments on the code. I think just especially with the like the Scikit-Learn functions and stuff and the classes, like obviously I think if in the book he explained everything, like it would take up a load of space, but I think just for me anyway, it was mainly just taking the code from the book and adding some extra info on like the parameters and stuff. But yeah,
definitely. And I also got the sense that like the main purpose of this chapter was just to give a high level view of the end to end, because a lot of times he'd be like, oh, and we'll review this better in a later chapter. So I'm kind of, so it definitely felt like it covered quite a wide and a really useful ground, but there were definitely a lot of details that had been sort of glanced over, I thought.
Yeah.
Okay.
Yeah, I didn't download the Jupyter notebook, and I've just realized that one of my questions that I had would probably have been answered if I had. So I better do that. I was like, oh, I'm going to do it. I don't know why, like somehow, I think just because, typing it myself makes it stick. It makes me think about it a little bit more.
I was going to say, because I created my own notebook, and then I looked at his notebook afterwards, and mine was obviously just pretty much identical to his, similar to what you were saying, just with a few additional comments and stuff. But I did find, though, writing it up helped a lot, and just sort of being like, wait, why are we doing this? Why is this here instead of here and stuff? So
yeah, there was a lot of that, and a lot of stuff that I think is probably just, for me anyway, was just that perhaps I would have written it slightly differently.
Yeah, and I mean, I guess
so. It took me a little while I found as I went through that I had less of an issue with that. I think I just got used to the style, and so I was comfortable with it. Whereas initially I was kind of looking at it going, like, in fact, the kind of first few lines seemed very kind of verbose. It just didn't seem like a very sensible way of doing it, or a very concise way of doing it, I suppose is what I mean. And then later on, I didn't worry too much, it's like,
no,
I mean,
I guess it's also like, I mean, most of the time there's not like one correct way of doing it, there's multiple ways, and I definitely got the sense that he was sometimes kind of trying to make everything maybe quite clear instead of kind of writing things as efficiently as he could have done. But,
yeah, I don't know, the thing that I didn't quite understand was he always, well, and it might just be because it makes it easier if you have bigger, like big projects or something, but there's always this line where he renames the function, and yet we only tend to use the function name like once or so, not very often. So I didn't quite get what we were doing.
Wait, which one? Do you remember where?
So every time we're importing these functions, so it's always import decision tree regressor, and then there's like tree reg equals decision tree regressor.
Yeah.
He like every single time he brings in a function, and I don't know if that's because he might.
So I think isn't that because he's initiating a new kind of object of that type? So he's like, even though it's called the same thing, he's always just so. And I think, like, I mean, a lot of times I got the sense, so a lot of the times I got the sense that he was also doing it just to make sure that if he had, because like you create a model and then you sort of you train it and stuff, so that you don't have any of the previous work hanging around. Like if you've trained some parameters or whatever, if you want to start anew, you make sure you just start them with a completely clean instance.
Yes, I think that's yeah. No, that's interesting. That's helpful. Thank you. I think maybe maybe it would have been good to include a little bit of that in the.
Yeah.
Or maybe he does that later. You know, a kind of best. I know there's a checklist, but there's maybe a kind of best practice thing would also be good. Maybe we get to that.
Yeah, I guess so. And I guess kind of just through reading it and being like, why is this being done this way? We'll hopefully together uncover the majority of the things that matter. Okay, I have prepared a slideshow.
Yeah.
Oops, go on.
Just add on before you start.
Mm-hmm.
Oh, sorry. No, I was just gonna make a quick comment. Yeah, a lot of I mean I think just like your question, Pamela, like I was thinking the same thing too when I first saw the code, but I did find just actually, you know, having a notebook and playing around a bit definitely sort of helped me understand what each bits are doing. So there were things that didn't click with me straight away, but yeah.
Okay, I might go fast through some of these bits, seeing as everyone's kind of gone through them. But yeah, I mean, as we've said, this chapter is very much looking at the sort of the end-to-end of a machine learning project, and the sense that I got was that it was just sort of making sure that we had the overall context for where everything fits in before we start focusing in on like what is this specific model or things like that. So the first bit, the framing the problem, I quite like this chapter because I definitely find a lot of data science kind of projects and things that I see online that just like train this model, but it's never said like why you're training the model, and you never evaluate whether that's even the thing that makes sense. I mean, I've definitely seen examples where people spend ages working on something really sophisticated, but then kind of realize they didn't need to do that because like the problem itself lent it to a way simpler solution. So the sense that I got was the main purpose of this part was to make sure that we're solving the right problem and make sure that we're using a sensible approach to do that. And as I'm sure you're all aware, the objective in this case was to create a district pricing model, which takes in some input data about district data. It predicts the exact prices as accurately as we can of the median housing price for that district, and then that's fed into another model for the downline, which does some investment analysis. And we were asked to look at what sort of problem it is. Oh, sorry, I don't know where the picture disappeared. And in this case, we were looking at a supervised problem, and it's a supervised problem because we have essentially a labeled data set. We have data about the district, and we know what the price is, so we can use those as labels to train a supervised model. It's a regression model because we want to get a number out. We don't just want to see like this is expensive or cheap or whatever. And batch learning because the data set is relatively small, so we can fit it all into memory, and there was no apparent need to kind of retrain it frequently. There was some discussion about what performance measure to use. And in this case, it was the root mean square error that the author suggested we use. This seems to be the most common choice for regression models. There's other choices possible, and I guess in reality, we might want to look a bit better at the data to see whether, for example, whether we expect to have outliers, because one of the comments was that this measure is quite sensitive to outliers, whereas other performance measures might not be so skewed by that. But in this case, since we don't have any obvious reason not to use it, it's kind of the most natural starting choice. After we've selected the performance measure, validate the assumptions, and then we're ready to get the data. So I thought there was quite a good section there about how to get started with Jupyter notebooks. And oh, actually, let me just move. I've kind of split the presentation up between a notebook and a slideshow. So let me just open up the notebook. Nice. Sorry?
Nice.
Oh yeah, yeah. I just figured there's so much like data analysis and stuff going on. It doesn't really make sense to talk about it all there. all in the PowerPoint. So I mean, the first few functions, I mean, this is all just stuff that's provided by the author. And conveniently, we can, in this case, actually just access the data from a site that he's provided. And we've got a function here to fetch the data from this website and to then load it from what we fetched into a pandas data frame. I don't think it's really worth dwelling too much on the details here because it depends so much where we get the data from. I mean, in most cases I've personally worked on, it's either been like reading it from a database or from like a comma separated file. So, I mean, this is just very specific to where the author has chosen to store this data. But the main point is that usually you would follow some sort of approach like this. You first fetch the data from wherever you're getting it from and then read it into the format that you want. And we can take a bit of a look at this data. And as we can see, we've got all the key variables that the author promised us. We've got some longitude and latitude. We've got some housing median age, total rooms, a lot of exciting information. And the key one that we're going to be or the only one that we're going to be predicting is the median house value. You know, there's a lot of things we can do to kind of get familiar with the data. Like we can look at how many records we have. And in this case, as we can see, it's a very small data set. There's just under 21,000 instances in the language of the user. No, sorry, of the author, I mean. And then we can also get some information. So I guess the key things or the key information that we'd probably want to get from this view is whether we are missing any data for any of the columns, because we know that if that's the case, we'll have to deal with that later. And that's just because most machine learning models don't deal well with missing data. So in this case, we can see we've got a fairly well populated data set where the total bedrooms is missing some records, so we can deal with that later. But the other ones seem to be fine. Another thing to note is that this ocean proximity is not a numeric value. So this is a string in this case. As you can see, we've got kind of near bay and other similar values there. So again, that's something we'll want to keep in mind when it comes to preparing the data for the model. And then at this point, the author pointed out that we should not look at the data anymore. I mean, he did do a few more kind of visualizations and stuff, but to be consistent with what the kind of message that he's teaching, I decided to leave it here because I guess the point he was making is that the more you look at the data, the more likely you are to recognize some patterns in the data. And because you want to make sure that you're not training or that you're not already making some assumptions about the patterns that you're going to find in the testing data based on what you've seen before you've actually kind of trained the model and tested it. We just leave it at this point and move on to creating the test data set so that we can then look more closely on the training part of the set. So going back here. So as a kind of a guideline, around 20% of the data set is usually a sensible proportion to set aside for the test data. He did make a mention saying that for very large data sets, we might not need that many records, but as a sort of a first, or as a kind of general rule, 20% is quite a good starting size. That said, we need to look at whether random sampling makes sense, because there are various ways to just randomly split the data into a test and training set. There's functions that do that for you very quickly, but we need to make sure that we're not skewing the data that we're training or testing on by doing that. And like in our case, because the data set is quite small, it actually makes more sense to go with a stratified sampling approach, where we make sure that we have representation from all key categories in the testing data when we're evaluating how it performs in reality. So now, once we've decided to do stratified testing, another thing to keep in mind is that we need to be able to find the same test set again in subsequent runs. And this is so that, you know, if we need to redo anything, we want to make sure that we don't lose track of this test test data set that we've set aside. So he outlines a few different approaches that we can use for this. And now I think we go back to the notebook. So first, I don't think we need to dwell too much on the first bit here, because this is just the random splitting, but this is just to kind of demonstrate how easily we can split the data if we don't care about having representation from everywhere. But because in our case, we know that the data set is small, we want to make sure that we have representation from all key subsets. And based on what the experts in our company said in this very real sounding example, they said that the median income is a very good predictor of the median housing prices. So if we want to make sure that our model performs correctly, regardless of what sort of scale the median income is on, we need to make sure that we've captured representation from all key categories. So first of all, we just look at what sort of values do we have here. Okay, great. We can see it's quite skewed to the left. So we've got quite a long kind of trail on the right here. We want to make sure that we have representation from all of them, or from kind of all, however we decide to split this data up, from all categories. But we also want to make sure that we're not splitting it up into too fine categories, because we can see how few instances we have in this sort of range compared to here, for example. So it wouldn't really make sense to be like making sure that we have an instance for 10 and for 10.5 and for 11 and for 11.5. So there's not really one right way to split this up, but the author suggested that we split this up into buckets of sort of size 1.5, where this is just this is obviously not US dollars, but it's it's a categorical unit, which roughly corresponds to, I can't remember exactly what the conversion rate was, whether it was like 10,000 or 100,000, whatever. So anyway, so in this case, we use Pandas cut function to just split our data set up by the median income value and using these predefined bins. So if we look at what this actually does, so these are median income values from the input data. And we can see that for each median income, we've now assigned an income category. And so, for example, category 5, that corresponds to the last bit here, which is from 6 up. So 8.3 falls into that bucket, whereas 5.64 falls into bucket 4, which is 4.526. So, so if we look at the histogram for this category, we see that it, is somewhat makes sense. It kind of corresponds to the graph above, or represents it closely enough. So now that we have now that we've established some way of splitting our data up by this important variable, we use the stratified shuffle split that is provided by Scikit-Learn. And we split our data into a stratified training set and a stratified testing set. So then lastly, just to assure ourselves that what we've done here has resulted in what we wanted, we look at the proportion of the proportion that falls into each of the categories. So if we look at, so the overall was, so that's for the whole data set. So this is including the testing and the training. We look at the proportion in each of these categories. In the stratified sample that we've created, we see that it's very similar, whereas the random one is kind of a bit more off, as we can see in the errors. We can see that the random error is typically a lot higher than the stratified error. And then lastly, before we go on, we drop this column that we just created with the category. And we do this in place, which means that we drop it from the data set itself. We're not creating a new data set. And I guess the reason why we're doing this is because we don't want to use it when we're training the model. I mean, that's a bit of an assumption. In reality, maybe this performs better than the actual number, but because we know that we want the output of the model to be a numeric value, which is as accurate as possible, it sort of intuitively makes sense to use an accurate number rather than a category for the number. But I guess if we were doing this in reality, we might want to introduce a hyperparameter at this point and kind of try out which one performs better. But for the sake of demonstration, we just forget about this for now. Any questions or comments or anything like that so far? No? Pace okay?
Mm-hmm.
Sounds good. Okay, on to, So on to number 4, exploring the data. So before we start looking at the data, just to kind of think about why we're doing that, we want to get familiar with the data we're trying to model. So this is just so that we can sort of apply some common sense when we're modeling. And we also want to spot potential problems or data quirks that we might need to account for when we're creating any models. And then lastly, we want to do some high-level discovery to see whether we can see any patterns in the values. So, a best case scenario might be that we immediately see that the median income, for example, is a perfect indicator of the median housing price, for example. So we're just doing like a bit of a discovery into this to see whether there's anything that kind of jumps out as being worthwhile looking further into when training a model. Back to the notebook. So we first overwrite this housing variable that we had created with just the training part of the set. And this is just done so that we are absolutely sure that going forward, we are only training on the training data and we're only looking at the training data. So now that we're sure that we don't have any of the test data in here, we can do a bit of exploratory analysis of this. So first of all, we've got various statistical properties for every single one of the attributes. One thing that I noticed is that the non-numeric one doesn't appear in this. And we can actually see if we do that one separately, I can't remember what the name of it was now, ocean proximity, I think. Then we get information, but we get slightly different. So I can't talk and type at the same time. We get slightly different information about this one. So because obviously things like the mean and standard deviation don't make sense for numeric values. So for strings. So instead we get the number of unique values, top, the first one, the most frequent, and so forth. So looking at this is obviously loads of information, and I don't think anyone would be expected to immediately be like, aha, this is the thing that matters here. But I guess there's a few things that we note. We can, for example, see just looking at the mean for the attributes that they're on quite different scales. And most machine learning algorithms, possibly excluding some neural networks, but kind of, I guess most of the most popular, or the models that you kind of start with first, don't handle different scales very well. So that's something that we'll wanna fix and kind of to align the scales better when we train the model. Again, we can see that the total bedrooms are missing some values. Other than that, there's not really that much else that I would take from this. But maybe more kind of easy to information that's easier to digest is this kind of visualization of the values. So here what we have is for each of the attributes, we have just plotted the values, plotted histograms for the values. So a few things that we see. I mean, a lot of the attributes tend to be sort of skewed to the left, so they've got quite a long trail of values on the right. We also have, quite obviously here, for the median housing median age and the median house value, we seem to have some capping at the end, because for any kind of naturally occurring data, I think this would be quite this would be kind of an unusual pattern to see. Usually you'd kind of, if it's falling down, you know, you'd expect some sort of coming up again, but you wouldn't expect this at the very last, as the last available value. So this sort of indicates quite strongly that someone has manipulated the data here. And I think in this case, the author said that whoever, or someone, I can't remember whether it was someone in the team or someone, probably someone anyway, had capped the values for these two, and similarly for the median income, even though that one's not quite as obvious as the other ones. And some suggested approaches to handle this were to either exclude these values or to try and get more accurate values, to try and go and gather data for these records that represent the real value. And I guess it depends quite a lot on how much time you have, because obviously the more data you get, the more accurate it's going to be. And also like how much you care, whether you want to predict the whole range accurately, or whether it's actually enough just to kind of look at sort of the most common values. So I guess in reality, we'd look at, you know, the context that we're trying to solve this in and the constraints that we have, and decide what to do based on that. So because the median house value is the one that we are trying to predict, we are especially interested in seeing how that one varies depending on other variables. And I guess, I mean, in this case, you know, the author has chosen some nice, pretty visualizations that fit this problem really well. I mean, for a different problem, it might be a completely different set of plots that we want to create. But the sense that I got is like everything down to here is probably something that would make sense quite generally for regression problems. But then this graph is very specific to this problem. So we want to look at the sort of data that we have and adjust it accordingly. But in this case, it's quite a nice way of seeing how the median house value, which is indicated by the color, how that gets higher as we approach the beach, what seems to be here. And yeah, the author has obviously spent quite a bit of time kind of playing around with the parameters. I don't think it's worth spending that much time diving into exactly what they mean. But I mean, if we just try to, you know, update something just to see what happens, we see that this, for example, looks a lot worse. And I think definitely when I've been plotting graphs ever in general, they usually don't look great. And it's like a lot of kind of iterating on the parameters and stuff before you get it to look sensible. So I think we're definitely, as with much else in this chapter, we're sort of presented with like a nicely polished final outcome here, which I think is quite nice of the author. Then looking at how correlated the variables, or I think he calls, well, no, I guess we can call them variables here because we haven't excluded the labels at this point. Looking at how correlated they are with each other. And I guess there's a few reasons why we might want to do that. So first of all, some models don't handle two columns that are highly correlated very well. So you could get a model that doesn't make a lot of sense because it's sort of trying to extract some of the information from the first variable and some from the second, when a better approach might be to just exclude the second highly correlated variable and just use the first one. And then another reason is that we actually want to look at the median house value, which is the one we're trying to predict. And we want to see whether there's any variables that immediately stand out as being closely correlated. And there's a few things. I mean, the median income, in line with what our expert recommended, it's very highly correlated. There's a few that kind of stand out as well as being correlated, as being kind of potentially good inputs, like the total rooms, and on the other side of the scale, the latitude. So we can kind of see anything that's got a positive correlation means that, you know, as the median income, for example, goes up, we expect the median house value to go up. Whereas on the other side, as the latitude goes up, we expect the median house value to go down. So this is just kind of, gives us a bit of an indication of how the variables are related. An important warning though is that this just captures linear correlation, and we might have various other types of correlation. So the author chose 3 variables and plotted them against them, well, all against each other. But if we focus in on this first column here, the median house value, we can see how the values of the median house value change as the values of the other dimension change. And similar to what we saw above, there seems to be a linear correlation here between the median house value and the median income. Less obvious patterns between the other two. And I think the author made a note that, you know, the more variables they have, the less sort of scalable this isn't very scalable. Like, you know, if you've got 12 variables, for example, it's very difficult to actually comprehend the graph or this sort of plot if you had like 12 by 12. So I guess a good approach would be to kind of focus in on ones that are likely to be good candidates. Or alternatively, what you could do is kind of, if we're doing this a bit more properly, kind of try a few different variations and see which one works best. So then lastly, focusing in on the most promising one, the median house value, we can see the correlation. The correlation is quite clear, but there's also a few kind of data quirks like this, that threshold that we discovered, and there's a few other lines. And the author made a comment that, you know, we would probably want to look into those more deeply in reality. But since we're just kind of doing a high level demonstration, we just accept this as is for now and move on. So moving on to the data prep. Oh. And the purpose here is very much just to make sure that the data is in a suitable format to produce an effective model from. And I guess by effective, I mean both sort of accurate and, well, I guess primarily accurate, kind of covers all different spectrums and ideally predicts fairly correctly for those different values. So there's a few different sort of steps in the data prep proposed. And I mean, I think all of these are pretty generic to kind of two regression tasks at least. So the first one is it's looking at combination of attributes, because in some cases, combination of attributes will perform a lot better than just the attributes in the input set by themselves. There's the separate the labels from the predictors before we start developing any models, because no one wants to find out that they've actually included the answer in the problem when designing the model. There's cleaning of the data, so things like handling missing data. And then we want to, because we know we have one column that's not numeric, and because most machine learning algorithms prefer to work with numbers, as the author said, we want to try to convert this categorical value to numeric values. And there's a few different approaches that in general could work to convert kind of strings to numbers. And specifically here, we're focusing on not just random strings, but categorical values. And in some cases, an ordinal encoding, so where we just choose like, you know, this value is mapped to 1, this value is mapped to 2. In some cases, that's going to work, but that implies a sort of total, it implies that the values can be ordered, which in our case is not really the case, because we have things like near sea, near bay, island, and there's no sort of intuitive way to order these in one single order. So that's not approachable in our case. So what we do instead is we choose something called one hot encoding, where for each of the values that we see, we create one column for it. And for every instance that has that value, they get a 1 in that column and get 0 in all the other columns. He also mentioned that there is representation could work here, but I think this is slightly more advanced. I definitely don't know as much about representation learning, so we'll cover this more in a later chapter, I believe. And And then, so once we've chosen how to deal with the non-numeric values, we look at feature scaling. And this is just because, as I said before, most machine learning algorithms require the values to be on a similar scale. And in our case, we're going to use standardization. There's no obvious, I for one, at least didn't see any obvious reason why standardization would be preferable than min-max scaling here. And I think in a lot of cases, again, unless you know that you have some outliers that could skew your results, you can kind of choose either one. Standardization, I guess, is quite common and probably more common. So we go with that one here. And lastly, a point that the author made is that wherever possible, we should try and implement functions instead of doing manual prep. Just because I guess if we do something once, we're very likely to want to do it at some point again. So having that, not having to repeat the work every time is in everyone's favor. So on to the data prep. So first, we start by creating the combined attributes. And in this case, I mean, because I guess we could combine the attributes in any way that we could. We could divide all the attributes by the the households, for example, or we could choose to like square every single attribute. But I guess we have to start somewhere. So the author has here chosen what I think are kind of sensible starting options, because we're trying to predict the value of the median value per household, but a lot of the data that we have is per district. So we divide the total rooms by the households. We divide the population by the number of households as well to kind of get data that's per household. And then lastly, just kind of, I guess, based on the author's knowledge, he kind of had a suspicion that the ratio of bedrooms to rooms could be a good indicator. And if we look at the correlation matrix, so this is just the same thing as we did before, but this time we've included these 3 new columns. We see that actually the rooms per household is doing pretty well. It seems to be pretty correlated with the median house value, and the bedrooms per house as well. And in all cases, they are more correlated with the value that we're trying to predict than the inputs were. So I think that's quite a nice demonstration that some kind of pre-processing and trying out different attribute combinations can be really beneficial. So then once, let's see what we're doing here. Okay, so then combining these attributes, or sorry, adding these attributes to the set. So the author pointed out that this would be a nice chance to use some hyperparameters, because these seem to be pretty correlated with the value that we're trying to predict. But at this point in time, we can't be completely certain that the model is going to perform better with these variables. So one of the things that was suggested that we could do is that we could try adding these, but doing it so that we can kind of switch it on and off as we're training the model, so that we can try different variations and see what works better. So this is very similar to what was done up here, but it's just been kind of parameterized a bit more. And this is the first example that we see as well of a custom transformation. And the author made a point that it would be, in general, very valuable to wrap any sort of steps that we're not completely sure whether we want to include, but think could be valuable, including them in a transformer like this. One thing that I thought was quite interesting is what Scikit-Learn considers to be a transformer. The fact that all you need to do is you need to have a transform method, a fit method, and a fit transform method. That as long as you had those 3 methods, it would be considered a transformer. Because I guess it's quite different from, for example, like typical inheritance. It's I can't remember what it was called, like doc typing or something like that, which was, I'd never heard that term before, but I think it's quite a good one. I think I looked it up and it said to me like, if it well, if it walks like a duck and it quacks like a duck, then we assume it is a duck, even though, you know, it could be something else, but it behaves so similarly that the way we're interpreting the world, we consider it to be a duck. So we separate the predictors from the labels so that we can use just the predictors for the model training. For handling the missing data, we have we use a simple imputer, which in this case, we use a median strategy. So that just means that whenever there's a missing value, we replace it with the median value of that column. I mean, there's loads of approaches that we could choose to populate these. Like we could use along a similar kind of approach. We could use like mean value or the most common value, or we could use a stratified approach where we try to split the values of the column up and try to find split the records of the data set up, find similar records and populate missing values with kind of the median value of the strata that record falls into. And we could even train a model to do this. But in this case, we are just gonna use the median value. And if we print out what the median, so this is these are the values that the imputer will use to populate any missing data. And just for some assurance, we've printed below what the median values of the columns are. And as we can see, they're an identical match, so we can carry on happily. And here we just, we transform, or we create a new object, I guess, called X, which is just the numerical values of the housing data, but with missing values replaced. So then onto handling attributes that are not numeric. We have, as I said, this ocean proximity field, which we have determined is categorical, and we're going to use the one hot encoding. And just to take a look at what this actually does, we see we've got 1, 2, 3, 4. Yeah, we've got 5 values. So we've got 5 columns here. And as you can see, each of the instances will only have 1 in one of these places. So for example, this record, it has 1 for the first category, which is less than an hour from the ocean. And this third record will be near the ocean. So we can we've just represented the same information differently. Feature scaling. So yeah, we're gonna use the standardized approach. And lastly, we put this all together into a pipeline. And one of the takeaway messages that I took away from this chapter was how powerful these sort of pipelines are. I mean, I'd never really used Scikit-Learn's pipelines before, but I thought it was quite impressive how you can create transformers and sort of mix and match them as you want and kind of run them all in one go, which is definitely quite useful when you want to kind of try out different combinations and switch things on and off and stuff without much manual input. And then lastly, we add the transformation for the for the categorical value. So now housing prepared is our set that's ready for a model to be trained on it. Yeah, this was the main takeaway that I took away from this chapter. Scikit-Learn is great. There's loads of stuff in there. It's thought about just about everything that you could encounter.
yeah, I was just glad to that. I did find, like, as I was seeing more and more of it, it seems so like cleanly and like clearly organized. Like, I don't know, it's quite impressive in a way.
Definitely a lot of work that's gone in there.
Yeah, because I think there are even sometimes, like, even without even looking at the text, I could sort of just guess, how to access the different data from the things. It's just so consistent, which as you say, I did think it was really good.
Yeah, but that's a good point, because it's both very it both covers a really broad range, but it's also really intuitive, which I definitely don't think go hand in hand. So I think it's really impressive that they've achieved both. Okay, on to selecting and training a model, which is what we all came here for, I imagine. So a general kind of guideline, the author pointed out that we typically want to select a few sort of best candidates. So shortlist kind of 2 to 5 promising models before spending a lot of time on them, on kind of on improving the parameters. And the best approach tends to always be start simple and then go more complex from there. Because obviously, if we can get away with a really simple model, then we can save ourselves loads of time and effort. So on that note, we start with a linear regression model, which I think is just the simplest regression model you can have. And we just look at how the model performs on a few instances of the training set. And yeah, I know training sets were, again, we're completely excluding the testing set. We're just looking at the training set. So, you know, we've got some values here. There's like, they're not ages off, but they're not super accurate either. So we used the performance measure that we had decided on, which was the mean squared error, and we get the score here. And I think it can be quite difficult to know what to do with this number, because you know, we know that if it's 0, that's too good to be true. If it's 1,000,000, that's obviously bad. But you know, what does 68,000 mean? And I think the author did quite a good point. Of saying that, you know, if we look at this in respect to what values we have in the data set. So in this case, we have values between 120,000 and 265,000 roughly. So considering that, if we're assuming that the error is going to be on average somewhere around just under 70,000, that does not seem to be very good if we look at the sort of the range of values that we have. So at this point, we can determine that it's worthwhile to look at other models. And we go, and as was covered in the first chapter, there's a few things we can do now. So we can either try adding more features, or we can try a more complex model. And either approach would work here, but because linear regression models are kind of, you know, they're only going to work well when if the data is very specific, if it follows a linear pattern and is quite sort of doesn't have a huge amount of outliers and things like that, we decide to go with trying a more complex model here. And we go with a decision tree regressor, and we get no error at all. So it was a very good demonstration of kind of the things that you can run into. As we know, this is too good to be true. So now we need to understand why this is happening. Is this happening because we're overfitting the training data, or is our model just amazing? And a common way to check or to kind of validate whether we're overfitting the training data is to look at a cross-validation set. So again, Scikit-Learn has a really handy way of checking here. So what we do in this case, we've split the data into 10 different subsets, and we iterate through them, and each go around, we leave out one of the 10 subsets, train on the other 9, and then look at the performance on the set that we've left out. And as we can see, we now get a mean error of 71,000. And if we compare this with the linear regression, we can see we're actually doing worse now on the kind of the cross-validation set. So at this point, we know that we're overfitting the training data. So we still don't have a model that we're satisfied with. So we go on to more complex model, and we try a random forest regressor, which essentially is made up from a collection of decision trees, and then there's some clever logic that combines them. And this is an example of ensemble learning, and I believe there's going to be coverage about that a bit later on. In terms of the kind of parameters here, oh, actually it's run already. Okay, I might make that comment anyway though. The N estimator, so I believe this is the number of trees in the forest. I think the final model, you could potentially end up with fewer if that's a better solution, but this is the sort of the starting number of trees, or estimators as they call it in their kind of language. And we set the random state here so that we know that we can get the same, so that we can get repeatable results. We calculate the same as we did before. We calculate the root mean square error on this using the cross-validation approach. And I think this might take a few seconds to run. Any questions or comments while we wait? No? Okay, I don't think it takes that long anyway, so we shouldn't be sitting here in awkward silence for long. I guess just talk about the things that are coming up. So yeah, there's for any model that we train, there's a range of kind of parameters that we have available for the model. So one of the ones we have available here is the feature importance. So we can actually see what the kind of, what's it called? What's the kind of the number that's linked to each of the features when we're running the model. And then we here have a kind of a combination of steps that combines these numeric importance values to the names of the features, just so that it's kind of human readable. And then lastly, we save the model. And this was something that the author made a point that we should save every model and we should save every version of every model, just because you might need to roll back at some point and no one wants to find themselves in a situation where they've lost all their work. So I guess just good practice, as with anything, make sure to save and save again and save everything that you could possibly want to use again at some point. I don't know why this is taking so long. This definitely didn't take that long last time when I was running this. But I guess we can go on to the into here. Key takeaway that I took away from this chapter, I guess kind of connected to what we were saying before. It's very intuitive. The syntax is very standardized. So I thought it was interesting to see that, you know, as we changed, for example, from the linear regression model to the decision tree regressor, the syntax is pretty much unchanged. I mean, there's some parameters that are going to vary, but in general, we're always following the same approach. We import the class, I guess it is. We create an instance of that model class, and then we fit it on the kind of the training data, given the labels. And then lastly, we can output. Oh, I think we just finished here. So yeah, we can see the importance, and we can see, so this is what our model will be using to actually make predictions. I thought it was really interesting. I mean, the first one doesn't come as a surprise at all, because we know the median income is important, but I thought it was quite interesting that inland had a positive score here. So if something is inland, we're saying that that increases the expected housing median price, which I thought kind of contradicted the chart that we had, where we saw that like by the sea, they're very expensive. But you know, I guess in reality, we might want to, you know, look at, you know, do all these parameters make sense? If not, do we want to try running it where we exclude some of these attributes from the input value? And do we want to see whether we get a more intuitive outcome? Or what could even be happening is just that, you know, we look at the data and we don't recognize that actually it's not as simple as just the kind of geographical coordinates having some impact by themselves. Maybe it's like a combination, like if it's inland and population per household or something like that, that the model is picking up, but it's not as intuitive to us. So anyway, there's a lot of things we could do with this information. Moving on to fine tuning the model. So at this point, we've decided on the type of model we want. And as the author said, in reality, we'd want to shortlist a few. But in this case, you know, because we're just doing this for demonstration purposes, we just have this one random forest model that we're quite happy with. And we now want to fine tune before we try it on the test data. So we can use, there's a few different hyperparameters that we could be kind of trying different values for here. So one is the N estimators, which is the number of trees in the forest. Max features, which is the maximum number of features that each tree can have. And then bootstrap, which according to the documentation it's whether bootstrap samples are used when building trees. If false, the whole data set is used to build each tree. So, so what this does is it iterates through all combinations. So it will try like n estimators 3, max features 2, and then next it will do n estimators 3, max features 4, and so forth, and look at how each one of them performs. We can obviously decide how we want to determine how they perform, and in our case, we use the performance measure that we had decided on before, and we end by printing out the best choice here, which is actually 8 features maximum and 30 trees in the forest. And we can access this best estimator here as well. And the author did make a point that, you know, n estimators 30 is the top, or is the highest level of n estimators that we tried, and max features 8 is similarly the highest value that we tried. So in reality, we'd probably want to try some even higher values just to see whether that performs better. But, you know, that would follow a very similar process. So we'll just move on here. I just noticed that we're up on time. Is everyone okay to stay for another, like, I mean, I guess we've got maybe like 7 minutes left. Yeah, okay. Otherwise,
yeah,
if you, okay. Otherwise, I mean, feel free to drop. I won't take it personally if people drop off the call. Okay, yeah, so looking again at the feature importance of this model, yeah, great. It looks pretty similar to what we saw before, slightly different parameters, but kind of similar attributes that are being used. So moment of truth, now we evaluate the model and we get this performance score, which is the best one we have seen so far. So we, oh yeah, sorry, I forgot one very crucial bit here. So we're actually testing it out on the testing set here, not the training set like we had before, because we have reached the point here where we have parameters that we're happy with, which are these ones that are listed, well, the parameters here, and here's the actual description of the model. So now we try it on the testing set and we get a score, which is, okay, it's not amazing, but one point that the author made is that this is higher than what we were seeing on the training data, which was somewhere up here. Yeah, I think this is the one. So we can see 18,000, well, just under 19,000 versus what we have here, which is just under 50,000. So we can see that because the performance is so different on the training versus the test set, we can see that the model doesn't generalize amazingly. So we are still over 50 in the training data. So at this point, we'd want to go back and, well, we'd want to review the different models that we have and kind of see, see whether we can do anything to improve things. We really need to be careful though, not to just at this point go back and fiddle more with the parameters, because at that point, we've already seen how it performs in the test set. So we'd be kind of biasing against things that don't perform well on the test set. And the whole point of the test set is to test how it generalizes on unseen data. So we'd have to do something else. Like we'd have to kind of look at maybe combining different models or like gathering more data or something that's more substantial and not just iterate in this sort of small loop here. And yeah, we can get the confidence interval as well. On to the exercises. So the first, well, a lot of these actually won't be able to run in the session just because they take ages to run, but I guess we can kind of talk through them. And the first one, we're supposed to do very much the same as above, but use a support vector machine this time. And use grid search CV to iterate through the different parameters to find the best type of support vector machine that we can for this data. And this is pretty similar to what was done above. So I guess the only real things worth pointing out is that, as we can see, the syntax is very similar. We create the model and and fitted the same way. And we have the grid search CV. The key difference here is just that the parameters are different because it's a different type of model. So in this case, we have, instead of the number of estimators that we had last time, we have the kernel of the support vector machine and this parameter called C as well, which has something to do with the learning rate, and gamma as well. And then we, again, very similar to what was done above, but instead of using a grid search CV, we're in this case using the randomized search CV. And the impression that I got was that whereas the grid search CV, it tests all different combinations of the parameters that we give it, the randomized search CV chooses a random combination. I wasn't really sure how well a job it does at kind of choosing randomly, but still kind of having some confidence of being close to the best solution, or whether it was purely random. And so what I took away from it is that the grid search CV would probably, I think, always outperform the randomized search CV if you have the ability to run both. But obviously, trying every single combination is ridiculously expensive if the data set is large. So I think in reality, that's probably not going to be possible usually. So this randomized search CV is probably a better choice for most problems. Third exercise was around creating a transformer that only selects the most important attributes. So at this point, we assume that we have the importance for all the features. So similar to what we calculated above for our best model. And out of those, we only choose the top K, where K is a parameter provided at the time of running. So we do this much as we did before. We have a transformer that follows the same pattern as usually. We have the fit and we've got the transform. And we, in the transform, we can see the only thing that we do is that we only include the feature indices, which have been decided by finding the top K features and finding the indices of those, where this is a kind of a helper function that we created here. And then we add this transformer to a new pipeline. So we take our full pipeline which we had before, and which includes all the things about, I can't remember what we were doing. It was scaling, filling in nulls, one hot encoder. And once we've done all that, we only select the top K features. I actually think this one might be able to run, so I'll just set this up now so we can, yeah. So, so as we can see, we only select, in this case, we set K to 5. So we only select the 5 columns which are most, which this transformer determines are the most important. And if we just compare that to what the data set, what the result for the data set is, if we use this kind of directly calculated top K feature indices parameter, we can see that we get the same result. And if we look at what features these are, these are all well known. We've seen these many times coming up as the top performers. So this is just kind of like an assurance check at the end to see that we're actually selected sensible parameters. And we've got their feature importance next to them. So fourth, combine the full data prep and final prediction into a single pipeline. So very similarly, we have the full pipeline, which does all the transformations of the that were done in the chapter. We have our new transformer, which selects the most important attributes. And then lastly, we have, we predict using a random forest regressor using the best parameters that we found before. And we might be able to run this. Let me see whether, oops. I remember how long this took. In this case, I had to update because we've been using 5, but that actually doesn't make sense here because for the best parameters, or the best model that we found selected 8 parameters. So I had to increase K just for this example. And then if we run this pipeline on some data, this was, I think it was just the top 5 records from the input training data. So these are the values that we predict for the top 5 or top 4, sorry, instances, and we compare it to what the actual labels are. We can see we're not ages off. It's, it makes some sense at least, and then we'd need to evaluate whether it's close enough or whether we need to do some more work. The last one was just pulling it all together. So we want to automatically explore some of the preparation using grid search CV. And I thought this one was the least intuitive one. There's a lot of I had to do a bit of Googling around what was actually, what this meant and what we're supposed to do here. But essentially what we're doing is we sort of traverse through all the pipelines that we've created here to, and try different values for the hyperparameters that we have available. So if we just look at the pipeline that we just created, which was the prepare and predict pipeline, this consists of the full pipeline, select the top K or most important attributes, and then the random forest regressor. So we see that this K feature, this is a parameter, a hyperparameter that we could, hyperparameter? Yeah, hyperparameter that we could try different values for to see whether we get better models. And if we look at this full pipeline, if we just remind ourselves of what's actually included in the full pipeline, this consists of 2 stages. So first there was the numeric pipeline, and then it was the one hot encoder. And if we look at the numeric pipeline, this was the imputer, which replaced the missing values. It was the add the additional attributes and the standard scaler. And the other parameter that we could vary here is the strategy parameter. So that's exactly what we've done here. For these 2 kind of free variables, for the 2 free hyperparameters, for the strategy and for the K features, we try a few different values. And something that I thought was kind of interesting about the syntax here, it's probably not going to make any sense when I recall this, but I recommend, I'll share the notebook afterwards, but I recommend reading this thread if you're interested in why this parameter is called this. But essentially what it means is that every double underscore means that we are actually accessing the attribute of a transformer. So for example, the prepare features, which is here, this is a name of a pipeline in this case. No, wait, sorry. Prepare features. Oh, sorry, this was not supposed to be. Oh, yeah, it is. Yeah, okay, sorry. So prepare features. This is the name for the full pipeline. And the full pipeline has the 2 parts, the num and the cat. And to access this num, we need to do 2 underscores. Go into the num. And the num is a name for the numeric pipeline. And to access the imputer name of the num pipeline, we again need to do 2 underscores imputer. And to access the strategy parameter of the imputer, we again need 2 underscores. That may or may not have made any sense. I don't think it's super important at this stage regardless, but I just thought it was kind of interesting. So at this point, we just through one single pipeline, we try out all the different values here and result with some model. And I think that's the end of what I had prepared. Any questions or comments?
That was very concise and very cool. Thank you for putting it all in the slides.
Thank you. I'm glad to hear.
Yeah, so it was really nice to have the code running as well as we go along. Yeah, I thought that was really good as well. Yeah, there was one thing that didn't come to mind when I was doing it, but it did as you were presenting it. Was actually going back to when we create the test set, and that this time we did a stratified sampling to get the test, to split the training and test set. And I guess here we did that because we had prior knowledge, and so that allowed us to basically make our test set before we did any sort of visualization or any looking at the training data. But I wonder if I don't know, maybe more of discussion point in the question, but let's say you don't have any prior knowledge about what how unevenly distributed you might be for some of your features, whether it's worth how do you know whether to just try random sampling, or would you have to train the model and see, okay, or once you look at the data and you see, okay, well, it's actually really unevenly distributed for this feature, so now I know that I'm going to try. That was one thing that came to mind that I'm not sure what the best approach is yet, but
no, I mean, it's a really good point, and I don't think there is one right answer. I mean, I think not speaking from a huge amount of experience here, but kind of from what I've read and kind of what I think. I mean, I think, there's a few different approaches you could take. Like, one is just, as you say, kind of, if you see your model is behaving really badly, and specifically if you look at the patterns for where it's performing badly, then you can go back and look at, oh, maybe I didn't, maybe I didn't have enough representation from this group here. So I guess that's one thing. I mean, another thing would be to look at, I guess try to gather insight, because I guess we never want to be in a position where we're trying to predict based on some data that we have no knowledge and no understanding of. So I guess trying to speak to experts, or even just do a bit more kind of data exploration yourself, which I guess would be kind of looking at the categorical values and seeing whether which values are categorical, and do I have really skewed data when it comes to the representation between the different categories. And I guess there's a few common ones, the one that comes up all the time is for example, gender, forgetting to include women in the test set, or forgetting to include certain ethnicities, and just think does the data that you're working with represent the real world? And I think it's really difficult to actually confidently say yes, but I guess you can try and look at the common pitfalls and try to avoid them. And that would be my my take on the matter.
Because I was going to say, because I think the example that was in the book about I think it was just a survey, and not having in your sample having it different to the population. I guess I think what you said sounded quite sensible to me, really. And as you say, I think especially with these sort of supervised problems, you're probably not going in without prior knowledge, really. So there probably is some sort of expertise to lean on, but
hopefully.
Well, you'd hope, and I guess it speaks to what you're trying to get across as well with how we're sort of building up our pre-processing and stuff and making it as modular as we can, because I guess you could get to the point where you say, okay, I've trained my first model with random, and then I want to go back and maybe try it again, and that's quite straightforward, but
Definitely. How did everyone find the chapter though? Do you feel like you learned a lot from it?
But I was struggling towards the end, just keeping track of everything. It was a pretty beefy chapter.
Yeah, it was quite a lot of ground covered. I also was really confused by because he kept being housing prepared, and I kept trying to go back, being wait a second, what does housing represent to this stage?
I was definitely losing track a bit of variable names and stuff. I think as well this chapter, I think there was a lot, so it definitely helped me when I broke it up a bit, and then over the weekend I sort of had a bit too much to do, and it was a bit trickier to get through the whole lot, but I think it was a really nice sort of introduction, I guess, just to the library as well and how to use it.
Definitely.
And I mean, and it's tricky with these sort of problems because this, he sort of invented the task we're trying to do, which isn't, necessarily, I think, we all do it, but it's nicer to sort of learn from, examples in your field and stuff like that.
Definitely.
But I don't know. Hopefully the format of the next chapter will be a bit, fairly similar. But I quite liked it overall.
Yeah, definitely agree. And I think while there's definitely some detail that's purposefully kind of avoided for the sake of simplicity, I still thought the author did a pretty good job on not not misleading us that it was always going to be, because I feel like one of the problems that I always have with, for example, Kaggle data sets is like everything has been cleaned so nicely, and it's really nice for like trying out techniques and stuff, but it's just so far removed from reality because, you know, you're always going to have like loads of missing data, and, you know, someone who just typed in, you know, 100 where they meant 1 and whatever. And so it was nice to kind of, I thought the author got quite a nice balance between reality and sort of, you know, not drowning us in details.
Yeah.
Cool. Okay, will we leave it there then? Thank you for staying behind.
That's all right. Let me stop the recording.